Right. As we solve this problem, which I consider a very difficult problem, as you can indicate, it's called a challenge problem, we begin with a very important statement. And the important statement is that this object is undergoing an acceleration. That acceleration is very important for us, because it's telling us that the total amount of force on the object, the net force, is a number, meaning it's not zero. And we know there's an overall force applied because that's what causes accelerations, a force. It also tells us that the F equals ma is relevant, again, because the amount of acceleration that the object is undergoing is dependent upon the force, and there's a relationship between the two of them. Now, Isaac Newton, in his genius, helps us here, because what he says is, if this is your setup, there's a checklist of things you need to know. And if you work your way through the checklist, you pretty much got what's going on. So what he would say is, you have an acceleration going on, so you better calculate that. There's going to be a force going on, and that force is due to gravity. He's going to say that there is a normal force, which is the force due to the compression of the atoms that make up this object, and they push back against the object being pulled down, and it counteracts the force due to gravity. He also tells us there is a frictional force that is in action here, because there is in fact two surfaces in contact with each other. There is something referred to as mu, which is the coefficient of friction, which is how rough the two surfaces are relative to each other. I'm going to write that a bit lower down here to give me some space. And then there's also an ending velocity. Now, Newton is going to argue that if you got all of these forces and motions figured out, you got it. That's what's determining the properties of this system. Now, also it's true, of course, is that the question has a list of items for you to further check off: acceleration, coefficient, frictional force, speed, etc. This also gives you an idea of what kind of things you need. Now, the checklist is very important and very useful because it lets you know step by step which equations and which issues you're trying to resolve. And so rather than having these equations come out of nowhere, you have a systematic way of going about solving them. Now, the first thing we want to know is this block is accelerating. And we need to know what is the rate of acceleration, because we don't know that. So when you have an acceleration, there's a number of equations you can use. You can have V final equals V initial plus AT. You have distance equals the VIT plus 1/2 AT. These are all equations that we worked with during projectiles and free fall, but they also are relevant to us for any accelerating body. So it turns out that the one that we can work with is that distance is equal to the initial velocity times time plus 1/2 AT squared. Now, since the initial velocity is 0, you see right here it says at rest, we can dump this. We know the distance is 2 meters, and it actually took 1.5 seconds. So if we punch those in, the 2.0 meters equals 1/2 the acceleration, and it's 1.5 seconds squared. If you punch that in, what you find out is that the acceleration is going to equal to 1.78 meters per second squared. Now I'm going to have to erase that and write it again because I know I'm going to have to use some of the space here later on. So if you don't mind, I'm going to have to squeeze that in a little better and say that it's 1.78 meters second squared. Okay, so we know that this value is 1.78. That is the acceleration. Now, in order to have accelerations take place, you have to apply a force. Inertia is objects will not move on their own. A force has to be applied. Now, what forces are acting here? Once again, Newton is so helpful to us. Newton would say, right, there is always a gravitational force here on Earth, and the force due to gravity is the mass of the object times the gravity. There is a normal force here, and what's interesting is you can extend the normal force down this way, and what that allows us to do is allows us to create a right triangle. This right triangle are the forces that are being applied on the object. Now, the object is moving that way. And it turns out that that's going to be the net force, also called the applied force. How do you know it's a net force? Well, because the object is accelerating down this way. In order for an object to accelerate over here, I got to have a force. And that force is the one coming down this way. But because it's moving down that way, there has to be a frictional force. And the frictional force is this. Now, before we all go nuts about this and say this is getting pretty hairy, Mr. Kurth, just hang in there. Take a look. There's a force due to gravity. There's a normal force. There's an applied force this way. We know that because that's the direction gravity is going to pull it. And then you have a frictional force. Those four items are what Newton said. Pay attention here. Do these problems, do these forces, because that's the ones that are acting on it. So we now have the acceleration of the object coming down. Now, what is the force due to gravity? The force due to gravity is going to equal to the mass times the acceleration due to gravity, which is g. So the mass of this object is 3 kilograms. Let's include our units there. Don't get too casual here. Times 9.8 meters per second squared. Now, the reason I wanted to make sure I punched out the units here is kilograms per meter, kilograms times meter per second squared. Those are the units that make up a Newton, and a Newton is a unit of force. So the unit of force of a Newton is 1 kilogram 1 meter per second squared. So you can see why these units would work very well for us. And so what happens is when you punch that out, you get the force due to gravity as equal to 29.4 meters per second squared. Now, what's the normal force going to be here? Now, the normal force, get my notes together here. The normal force on this system is solved the following way. This is a right triangle with 30 degrees here. If in your mind you can imagine I flip that triangle over and make this right angle sit there, that would mean that this is 30 degrees here. So if I want to solve for the normal force, that normal force is going to be this right here. Well, to solve for that, what I'm going to do is I'm going to take the cosine of 30 equal to adjacent over the hypotenuse. But the hypotenuse is the force due to gravity. Therefore, sine 30 times the force due to gravity, which is 29.4, that's going to give me the normal force. But Mr. Kurth, you are a foolish man. You said cosine, but in fact you wrote sine. Bad, bad, bad. So how about we correct that? This is cosine of 30, and when you do that, you get a normal force equal to 25.46 newtons. And if you want, Mr. Kurth again is being careless. We don't want this as meters per second squared. Come on, Mr. Kurth. Get your head in the game. You're going to have newtons of force for gravity. You're going to have newtons of force for the normal force. Now comes something that's a bit dodgy. Which is the frictional force. Right. Now, what we're looking at is an interest in solving for the frictional force. And ultimately, what we want to solve for is the coefficient of this friction. Now, this will come across a bit hairy. And that's okay. Let's explore how we're going to approach this. When I see frictional force, I think right. I think frictional force is equal to mu F normal. Oh, that's simple enough. Then we go, okay, I don't know my frictional force. I don't know my coefficient. But I do know my normal force, which is 25.4 newtons. I have a problem. And the problem is, I don't know that, and I don't know that. So now I have to get another equation that's going to let me solve for this. And at this point, for some, myself in many ways included, it's a bit like, dude, where'd you come up with that? And the answer is, it's kind of by experience. One kind of starts to say, you know, you work enough problems and you get to see it. So I'm going to try to change my color here. I've never done this before. Here we go. You say, okay. All right, let's find out. So what I'm going to do is I'm going to generate another equation in effort to find out about that. Oh, cool. It's all red. So here's my equation nested inside the equation. My total net force is equal to the amount of force that I'm applying because it's accelerating, but it's always being held back by my frictional force. Ah, there's that and there's that. But do I know my net force? I do. My net force is the amount of force that is creating the acceleration that I desire. Well, look at that. That net force, I'm up here now, my net force is equal to the mass of the object, which is 3, and the acceleration, which I calculated, which is 1.78. So what is the overall force that is being applied here? The answer is the overall force is a negative 5.34. And that came from here. But remember, that's the overall net force. The amount of force that is pulling it down is being countered by the force that is pulling it up. The down force, which is the applied force, is winning. How do we know that? Well, it's accelerating that way. So it must be greater than the amount that it was. Well, how much is that applied force? And the applied force, which is this one, is this one. So I take the magnitude of this one and say that it's the magnitude of this one. Well, what is that? Well, what that is, it's going to be opposite over the hypotenuse, which is sine 30 times the hypotenuse, which is the magnitude of the force due to gravity, which is 29.4 newtons, minus the counteracting force, which is friction. Again, let's think about that one more time. The overall force is going to be the applied force minus the force of friction the other way. Since it's accelerating, this one must be moving, so it's greater. So I take the difference between those two. When I, in fact, crunch the numbers, I find that my frictional force is equal to 9.36 negative. So my frictional force is negative 9.36 newtons. Now, what about my coefficient of friction? Well, that now is this one over here. So my coefficient of friction, just for kicks, I'm going to change my color back again. My coefficient of friction, which is going to be mu, is going to be equal to, here's my equation, frictional force equals mu normal force. So my frictional force is negative 9.36, which is equal to mu times the normal force, 25.46, and what I find is mu is equal to 0.37. Now I'm going to take a moment here, erase some of this, so we have more work space. Right, a little bit cleaner now. So we are now in a position to finally solve for now the ending velocity. Now, the ending velocity is going to be equal to the final velocity squared times the initial velocity squared plus 2AD. So we have the initial velocity is 0. The final velocity is what we are seeking. We have a distance of, an acceleration of 1.78, and it accelerates over a distance of 2. When you crunch it, your velocity is 2.67 meters per second. So I'd be the first to tell you it's hairy, but I would like to again try and emphasize to you the key to this problem was to have created a diagram, created your checklist. Often the question itself helps you with that, and recognize that there are these basic 4 forces that allow you to determine all the things that are going on in that system. And then what you do is you just go through your punch list and solve for each one. And that's how you come up with this long list of crazy equations, but you're solving for these very specific items that you're looking for. There you go.